Hello everyone, in today's video we'll be talking about decentralized file storage tracker on Rootstock. So before diving into that, let's understand what Rootstock is. So Rootstock is a smart contract platform that is built on top of the Bitcoin blockchain. It aims to extend Bitcoin's functionality by enabling the execution of smart contracts similar to what Ethereum does. Rootstock achieves this by utilizing a two-way peg mechanism that allows a Bitcoin to be converted into RSK tokens and vice versa. This integration allows developers to create a decentralized application that benefits from Bitcoin security while leveraging the flexibility of smart contracts. Let's understand the key features of Rootstock. So, Rootstock is an EVM compatible. Rootstock is compatible with Ethereum virtual machine, allowing the developers to easily port their existing Ethereum dApps to Rootstock platform without significant modifications. This compatibility fosters a broader ecosystem of decentralized application and services. And Rootstock supports smart contracts, enabling the developers to create a complex application that can automate processes and facilitate the transaction without any intermediaries. Then we have decentralized finance in Rootstock, which incorporates DeFi functionalities, making it a versatile platform for developers and users alike. It's also scalable by utilizing the sidechain. Rootstock addresses some of the limitations of Ethereum network, such as high gas fees and low transaction times, providing a robust environment for building and deploying the decentralized application. Now, let's go on understanding what actual IPFS is. So, IPFS is an interplanetary file system, which is a peer-to-peer decentralized storage protocol for storing and sharing data on internet. Instead of storing files on a single server, IPFS stores them across multiple computers, making the data censorship resistant, tamper-proof, and permanent. Let's understand how the IPFS works. So we upload a file, the IPFS breaks it into small pieces called as chunks, and then each chunks gets a unique hash called as CID, which is a content identifier. And this CID consists of numbers, uppercase, lowercase letters, and then the file is stored on several IPFS nodes across the network. When you or anyone else requests the files, the IPFS retrieves it using the CID, not the URL. So instead of seeing that HTTPS colon slash slash, we can see IPFS colon slash slash and the CID. So the key benefit of IPFS is that even if one node still has your file, it will remain retrievable, no central point of failure. So basically its flow is that you can add the photo PNG to IPFS and then IPFS will return a CID and now anyone can fetch your file via IPFS gateway or the local node. Now let's understand Pinata. So Pinata is a pinning service for IPFS. So while IPFS is a decentralized, the data can disappear if no one keeps or pins a copy online. So that's where Pinata comes in. So what pinning means? So pinning means telling an IPFS node to keep a file permanently stored, preventing it from being garbage collected. So even if no one else has your file cached, Pinata ensures it stays accessible. What exactly Pinata provides? So it has a permanent storage that keeps your file pinned for 24 into 7 on IPFS nodes. Also, it has fast uploads and retrieval that uses their infrastructures to make IPFS more performant. Then it has API and SDK together that gives an easy integration into your apps that can upload, fetch, and manage files. Then there is an accessible management which can manage the private and public files, getaways, and it also tracks the file usage, bandwidth, etc. So when IPFS and Pinata are together, if we see, the role of IPFS is that it has a decentralized file storage and content addressing There's a Pinata keeps your IPFS data always available. So IPFS is a protocol and Pinata is a service that is built on top of it. So it has many real world use cases as well, like NFT metadata for storing image and JSON metadata for NFTs, decentralized apps, Web3 social media for content persistence for posts, images. Then it has immutable archives, which has verifiable data logos. Now let's go on building an IPFS file storage, the app on Rootstock. So what is what it is exactly? So it's a decentralized file storage app that uploads files to IPFS via Pinata and stores the IPFS hash and metadata on Rootstock blockchain. So its main goal is to provide an immutable records of files with owner control deletion and clean web UI. So what all prerequisites will require for it? Let's understand that. First will be Node.js. So Node.js is a open source cross platform for JavaScript runtime environment that just let developers create servers, web apps. So here on this website, you can go and get Node.js. You can click here and download the Node.js from here, whose version has to be 18 or higher than that. Then also we have NPM. So NPM actually comes with Node.js only, as it's a standard package manager for Node.js. Then we have Foundry. So we'll require Foundry as well. So Foundry, the Ethereum development framework. So you can follow the step to download Foundry. You can just paste this command to your terminal and then Foundry up, and just you can install the Foundry accordingly. So the complete guide is mentioned on this website. Then you'll also require Git. So this is the website of Git. You can just go download Git from here. Git is a free open source distributed version control system that is designed to handle everything from small to very large projects with speed and efficiency. So you can just download Git from here for Windows and Mac OS accordingly. Then we also require some accounts and services. So go to Pinata and just log in here, sign up, and this will be useful for IPFS storage. So just create an account in Pinata. Then we also require a wallet. So just go to MetaMask here, metamask.io. The website will be open here and just view MetaMask web, and you just download MetaMask if you don't have any wallets. So you will have MetaMask and you can just connect the MetaMask. Then just go to chainlist. So in chainlist.org, include testnets and write here Rootstock Testnet. So you'll see, and you just have to add it to your MetaMask. And then to get the gas fees, to get the RBTCs, go to Faucet, Rootstock Faucet. You just need to go to Rootstock Faucet. So just go here, Rootstock Faucet, and just paste the address that you'll get from MetaMask. Here, once you created a wallet, you'll get the wallet address. Just paste it here and get the test RBTCs, which will be required as in gas fees for running or deploying the project. Then go to Wallet Connect, as we'll also require a Wallet Connect project ID. So there's the Wallet Connect website. Go on to it. Then here you just log in and your project ID will be displayed there. Just copy it and we'll be using it further while building our project. Then you should also have an code editor like VS Code or Cursor, which will have all the Solidity extension. So you just go to VS Code here and you can just download the VS Code for Windows, Linux, Mac accordingly. Now, our actual DApp, this decentralized application, will consist of two main parts. First will be a smart contracts, that will be Foundry, and the second one be front end. So let's go on building and setting up project. So this here, in this we'll create one folder and we'll name it as contracts, and we'll open our terminal. In terminal we'll open git bash. So Here in git bash, we'll give cd contract and then we'll run forge init, and now it will install all the foundries and dependencies that are required. So forge, so it's just installing all the dependencies. Here it will take a little time. Okay, once so it's done. Now now we have all of the folders in this. So the Foundry is a powerful, fast, and developer-friendly toolkit for Ethereum smart contract development that is written in Rust. It's similar in purpose to Hardhat or Truffle, but it's quite much faster and more modular to it. So let's go on understanding this. What all we have got. So we have foundry.toml. So this is a main config file, compiler version, optimizer, libraries, and paths. Then we have library, which is a folder for external dependencies that is installed with this Forge install. And then inside that we have Forge std, which is a Foundry standard library with testing and scripting utilities. Then we have src, which contains all your smart Solidity smart contract. Here we have counter.sol. Then we have in counter.sol is an example of contract created by default. Then we have test. Test is a folder for Solidity based unit tests, which have counter.t.sol, which is an example test file for counter.sol. And then we have script. Script is a folder for deployment and automation scripts written in Solidity. Inside that we have counter.s.sol is an example script to deploy the counter contract. So now let's go on creating our smart contract. Now let's go on deleting the default contract in src is counter.sol, and now we'll create a file in it and we'll name it as FileStorage.sol, and we'll go on writing a smart contract in this. So stdx license identifier MIT. Then we'll give Pragma Solidity the version at 0.8.19, and now we'll give contract. So this is a smart contract for storing the IPFS file hashes on rootstock. So we'll name the smart contract our contract as file storage. So this contract will allow the users to upload file metadata to IPFS and store the hash on chain. Now let's give event file uploaded, and this will be emitted whenever a new file is uploaded to IPFS and stored on chain. So in event, we'll give the address indexed uploader. This will just give the address of the user who has uploaded the file. Then string IPFS hash for the IPFS ID, which is a unique hash of file. Then string file name, which will give the original name of the file. Then uint 256 for the file size. I will display the size in byte. Then uint 256 timestamp, so we can get the time when the file was uploaded, and uint 250 ID, which is a unique on-chain ID. Now we'll give another event file deleted. So this will be emitted when a file is deleted by its owner. So file deleted, and this will have address indexed owner, and then we'll have uint 256 index file ID, and we'll have the string IPFS hash for the IPFS hash of string IPFS. Now we'll do the data structures and create struct. I'll name it as file info, and this will be a struct that will hold all the metadata about a file. Now, and this will have string IPFS hash for the IPFS content hash. Then we'll have string file name, string file name. Then we'll have address of the uploader. So address uploader. So this will just give the address of the uploader. Then we'll have UN256 for the timestamp, like when the file was uploaded, so we can get the time of it. And then the bool exists. So this will just be a boolean flag to check if the file exists or not. Now we'll give the state variables, and now we'll do mapping. So mapping from UN256, so it will map the file ID to the file info. So UN256 to file info, and the public files. Then we'll again do mapping for mapping from user's address to the array of fields file ID that they are uploaded. So UN256 and the array public to user files. Then again mapping from string to boolean, so it will be checking if the IPFS hash has already exists or not. So to avoid duplicate copies. So from string to bool, and it will have a public as IPFS hash exists. IPFS hash exists. Then we'll have UN250 public total files. Total files. So this will just give the total number of files that have currently been stored. Then we'll give UN256 public. That will have next file ID. So all the next file IDs will be assigned there. And next file ID. Then now we'll give the modifiers. So modifier as only file owner. This will ensure that the file owner can only perform the certain actions like deletion. Then this will have UN250. Then we'll give require, and that will have file ID dot exists, and it will display it as file does not exist. So I'll write as file does not exist. Then another require, similarly we'll write files, and inside that we'll have the file ID uploader, and this will give as message dot sender, and it will display it as not the file owner, not the file owner, and then underscore semicolon. I will again give a modifier. So this will be a modifier valid field ID, valid file ID. So this will ensure that a file with given ID actually exists before executing the function. So this will give our file ID, and this will give require. Similarly, we'll write the file underscore file ID dot exist, and if it doesn't, so it will give and display it as file does not exist, and we'll end it off. Now we'll upload the file. So we'll give a function as upload file. So this will upload a file's metadata to the blockchain, and we'll give string memory IPFS hash, and then we'll give string memory file name. So write string memory, and we'll give the file name to it, and then we'll give UN256, and which will give our file size. And now we'll give our external, and now we'll give our require statement. So this will just do the validation that will check to prevent the invalid uploads. So require, inside this will have the bytes IPFS hash and the len of this has to be greater than 0, and if it is so, then it will display it as IPFS hash cannot be empty. Then if again we'll give required, and if this bytes of IPFS hash whose length is greater than 0, so the file name cannot be empty. So we'll give here bytes file name and whose length has to be greater than 0. If not, it will display that file name cannot be empty. Then another require in which will give the file size which has to be greater than 0. Has to be greater than 0. And then if it is there, it will display that file size has to be greater than 0. This must be greater than 0. Then in another require will give the IPFS hash access. So require inside that will give IPFS hash access, and will give in this will have IPFS hash, and if it is not, then will display it as files with this hash already exist. So files with this IPFS hash already exists. Now we'll give the uint I'll give the uint 56 file ID. So this will just assign a new file ID equal to will give new file ID or next file ID. Now we'll create a new file info and store it in mapping. Inside we'll have file ID that would be equal to our file info, and then we'll give our IPFS hash in it. So IPFS hash will be, then we'll give the file name. So file name, similarly that will be given it as file size. Then uploader, that will be message.sender, and our timestamp. When the file is uploaded, that will be blog.timestamp. And we'll give another one as exists as true. And then we'll now give user files that will track all the files under the uploader's account. So user files, message.sender dot push file ID, and now we'll give IPFS hash exist. So that will mark this IPFS hash as used. So I'll give here IPFS hash exists. This inside I will give an array and underscore IPFS hash that is to be true. So this is equal to true. Now we'll do increment for the next file and total file count. So we'll write it here as next file ID. So this will do the increment, and also we'll do it for total files. And now we'll give emit. So this will emit event for front end and for off-chain indexing. So emit file uploaded, and in this we'll give a message.sender IPFS hash, then a file name, the file size, also the block timestamp, and final the file ID. Give the function as delete files, and in this will give uint 256 the and we'll give an external as only file owner, so this will delete a file which only an owner can delete it, and we'll have the file ID, the ID of the file that has to be deleted. So and this will have the file ID. Now we'll give the string memory. So this will retrieve the IPFS hash before deletion. So string memory, IPFS hash, and we'll have the files. Inside it will give file ID dot IPFS hash, and then we'll just remove the file ID from the user's file list. So uint 256 And we'll have storage user file list. So user file list, which is equal to the user files. And inside that we'll have message.sender. Now we'll give a for loop. So for uint 256, then this will have initialize I equal to 0, and this I has to be less than user file list dot length, and we'll do the increment of I so I plus pass, and then we'll give if statement. So if user file list the I is equal to, we'll check whether it's equal to file ID, then we'll give user list. So this will simply replace the related ID with the last element and then just pop up the gas efficiency. So this user file list is equal to user file list, and this will have user file list dot length minus 1 minus. Now we'll give user file list pop, so that will just pop it. So that will just pop up for the gas efficiency and then break. So now we'll give the IPFS hash exit. So we'll just mark the file as deleted and remove the IPFS hash from the active records. So IPFS hash exists, and then this will give IPFS hash, and which is equal to false, get as false, and also the files in file ID dot exist will be false. Now we'll just decrement the total count, so total files minus minus. I will just emit the file deleted. So now it will just emit event for UI and tracking. So file deleted message dot sender. Then we'll have the file ID and the IPFS hash. Now we'll just read the functions. So we'll give another function as get, and it will have our file ID in it as uint256 and the file ID. Now we'll give external view, and we'll have the valid file ID, which will have the file ID into it. Then it will returns, and it will return the file info memory, and now it will just return the file, so return files and the file ID into it. Now we'll give another function as get users file. So this will get all the files uploaded by specific user. So function get user files and the address of the user, address, ID, external view, return view, then returns, and it will return the memory like uint 250. Then it will also return the user file, and it will have the user. Now we'll create another function to it as get users file count. So and in that we'll give the address of the user. So address user. So this will get the total number of files that are uploaded by the user and also the user address of the user. So we'll give the external view, and it will returns 256. So it will return the number of files that are uploaded by the user. So return user files and the users that is. Now we'll give one more function as get files. So we'll give the function as get file. This will get the file information from multiple files. So get file, name it as get files, and then we'll give uint 256, then memory, and the file IDs. So file IDs from multiple files. So external view, and it will return. So it returns an file info, So now file info memory. So its result will be file info memory result that will be equal to new file info, and the file IDs dot length. So the file IDs from the multiple files. Now we'll give for loop again. So this will be loop to provided IDs and fill the results with existing file. So for UN256, I equal to 0. So we initialize the I to 0. I has to be less than the file IDs dot, and we'll just increment it IPFS, and now we'll give if statement. So the file and the file IDs, ID, and it will have I exists dot exists. Then the result will be, so result that will be equal to files and the file ID. So now after this will return 0. Sorry, that will return results. Now another function for to check the file existence. We'll create a function as file exists and our file ID into it. So this will give an external view returns the build. So it will just tell it in a true or false manner whether the file does exist or not. So the file ID dot exists, and now we'll give one more function. So we'll define a function named as get stats. So function as get stats. So this will give the contract statistics. Now I'll give the external. So it will return all the total files, the total number of files that have been stored. So returns the event 56, and now it will return the total files and the next file ID. So we'll give it in return total files and the next file ID. So we are done with our smart contract of FileStorage.sol, and now we'll go on further doing tests. So in contract and test, delete this counter.d.sol and create a file in test and name it as file storage dot. Now let's just go on typing a test file. So spdx license identifier mighty Pragma Solidity, give it at 0.8.19, and now we'll import. So this will import the Foundry's tests and consoles for debug console, and this will take it from Forge STD and the test.sol. Now again we'll import the file storage see FileStorage.sol, so it will import the contract to be tested. So storage.sol. Now we'll create a contract and we'll name it as file storage test. So this is a file storage test which will be a test contract for verifying the functionality of storage file storage dot. And this will give file storage public file storage, and then we'll test either user's address. So we'll give address public and we'll give user one. So this will create using Foundry's helper and make address. So user one equal to make address, and inside that we'll have the address of the user one. Similarly, we'll do it for user two as well. So address public user two, it will be equal to make address of user two. Now we'll create a function as a setup. So function setup public. So this will set up a function that will run before public file storage equal to new file storage. Now we'll create another function for test upload file function and we'll name it as test upload file. So this will upload a single file and validate its stored metadata. So public and I'll try it vm dot graph. So this will just simulate user one calling the function. Then we'll give file storage dot file. In this we'll give our test hash. So test hash 123 and then it will display test dot txt 1024. Now it will fetch all the total files and next ID. Then this will give UN 256 total files and UN 256 in which will have the next file ID. That would be equal to file storage dot and then now we'll assert EQ. So this will assert that one file that was uploaded and the next ID is increment total file comma 1 and similarly we'll do this for our next file ID comma 1. Now we'll give file storage memory. So this will actually retrieve the uploader's file data. So storage dot get file and this will give 0. So now we'll have again all the assort equations. So this will validate the metadata matches expected all the values or not. So we'll check it. So file dot IPFS hash that would be equal to m test hash 1 2 and then we'll similarly give assort eq and now we'll write it for file dot file name and this will give the file name as take the name as test.txt that we've already mentioned. Then similarly we'll do it for file size. So file dot file size and this will be given as 1024. Then we'll do it for files dot uploader. So this will give the user one comma user one and then we'll have a sort true. So this will check the file like this. And now let's give another function and name it as test delete file. Test delete and make it public. So this will delete files and verify the removal. So and public let's give the bank use and this will just user one will upload its file to it in a storage dot upload file that will give the QM test. So QM test hash 123 and we'll get the IPFS hash, the file name that we have mentioned test.txt, also the file size that we have given 1024. That all will be mentioned in this. Now let's go for confirming the file count before deletion. So for that the name went to 56 and the total files before and we'll give equal to file storage dot get stacks and we'll give assort equation here assort q and all the total files before so one dot and so this will have now we'll give file storage dot delete files. So this will just delete the files and now we'll give UN256 files after. So the one that we done was for before. Now we'll just confirm the total count that decreases. So here we gave 1. That was for increment in file count. Now this will do it for decrement, so it has total files after that would be equal to FileStorage.get similarly how we have done here earlier, and then we'll give our assert EQ, which will have total files after, and as is per recommends, we'll give it 0. So this will just confirm the total file count decreases. Now assert false, already given for assert true, so assert false, that will check that the file does not no longer exist. As we have deleted the file, it shouldn't exist after deletion. So just to check that, we'll give assert false file storage, and that will have file exist. And now we'll create function as test cannot delete other file. So we have checked this. Now let's go on creating the function as test cannot delete other files, and the public, and this will have a VM. So I will give this again VM bank, and now this will be for user 2 as you have given for user 1. So user 1 first will get for user 1 first, and then for user 2 user 1 file, and then this will give IPFS hash, then the file name as s.txt, then we'll give it for user 2 now. As user 1 have uploaded the file, now user 2 tries to delete the user 1's file that has been uploaded. So it should revert it. So vm.bank. And now we'll wait for user 2 to see if user 2 tries to delete the file of user 1. Then it should expect a revert and not the file owner, and it will display it as not the file owner. Now it will give file storage dot delete and 0. So here it has seen that if user 2 tries to delete the user 1 file, so it should revert those file and display, not the file owner. Now let's give another function, and I'll name it as test cannot upload duplicate hash. So test cannot upload duplicate hash. We'll give it public, and in this now we'll give VM dot rank and the user 1. So now user 1 if uploads a file with a certain IPFS hash, so user 1, and then similarly we'll write file storage dot upload file, and inside this will have the qm test hash 1 as test.txt, and the file size that we have given as 1024. And now if the user who tries to upload another file with the same hash as user 1, then it should again revert it. So for that we'll give vm.rank and user 2, and then we'll have vm.export expect revert, and once it reverts, it will display it as file with this IPFS hash already exists. Then we'll give file storage dot uploader file, and this will have qm test hash 123. And now here we'll have another txt. The file name would be another of the one that user 2 will upload. Here we have to see that the file is other, only qm hash. Similarly, here we'll have only qm test hash, another tag, another .txt, and let the file size of it be 2048, the one of the file that user 2 has uploaded. So that's it. So this is our test file, and now let's create a deployment script. So go to script, delete this default counter.s.sol, and we'll create one more file in this script, and let's name it as deploy.s.sol. And now let's start writing the code in this script. So let's begin with SPTX license identifier, and we'll give Pragma Solidity 19, and now we'll import the script and console. So import script and console from forge std script.sol. So this will import the script and console from the Foundry standard library. So this script will give the access to Foundry's scripting environment for deployment, and this console will be used for logging useful information during script execution. Now again we'll import file storage. So this will import the file storage contract that we want to deploy. src FileStorage.sol. FileStorage.sol. It will import it from that file. And let's create a contract and name it as deploy script and script. So this will define the deployment contract. The Foundry runs this contract when executing a deployment script. So in this we'll give a function setup and make it public. So public. So the first is optional setup function that will run, and you can use it to initialize variables or read the configuration values if needed. Then we'll have function run. So the main function that executes is the deployment logic. This function runs when you execute the script using for script. So we'll give function run public and then write UN256 and the deployer's private key. Deployer's private key, which will be equal to vm.env event. So this will load the deployer's private key from the environment variable inside this private key. So the Foundry allows accessing environments variables using vm.env helpers. So we have given it. Now let's give vm.start broadcast. So this will start broadcasting transactions using the provided private key, the deployer's private key, and this will have the deployer's private key. And so from this point, all the contract creations or the state changes will be sent on chain. Then we'll have file storage and we'll name and we'll give it as a new file storage. So now we'll stop the broadcasting here. So vm dot stop broadcast. So this will stop broadcasting. Any code after this runs locally only. Now we'll give console.log, and it will display as file storage is deployed to, and it will give the address of the address of the file. And again console.log, and this will display the deployer's address, and this will give vm dot address of the deployer's private key. So deployer's private key. So here our script is done. Now let's go on testing our smart contracts. So open terminal and just go and git bash. Just give cd contracts and give purge build to compile the contract. So now it's just compiling all the contracts. I've just opened my git bash, and now let's go on running a script and command as cd contracts. Then I'll just export my private key here. So export private key, and you just need to enter your private key in this. As it's confidential, I won't enter my private key. Now let's give for script command. So for script and Deploy.s.sol, and then here we'll just enter as deploy script, and then we'll give RP URL, and we'll just give as https and public node.testnet.rsk.go, and just broadcast So now just enter, and here now our contract will be compiled and run. It's compiling, and now we'll just see how our contract will be compiled. So the script has ran successfully, and here we can see our file storage is deployed to this address. So we can see from where our contract is deployed to, and we can also see the deployer's address. Here we have chain 31 as I have used testnet, and now it's just further compiling. So we can see all of this as estimated grass size, and now it has just successfully compiled our contract. So we can see hash, contract address, and everything here. So in this video, we have seen the deploying of contract. In the next part of this video, we'll be integrating with the front end and we'll be writing the front end code. Till then, thank you. Happy coding.